Well, I'm honored to get to talk to you guys again. It's always fun to talk to this group and to begin to build these relationships between and deepen the relationships between computer science and economics. I really appreciate that the Simons Institute is sponsoring this. What I want to talk about today came out of a consulting project. The title is Adverse Selection and Auction Design for Internet Display Advertising. And I have a couple of co-authors, Nick Arnosti, who's, I don't think he's here today, graduate student on the job market this year, and Marissa Beck, who's a graduate of the Stanford economics program. I actually began this with Marissa, and Nick made enormous contributions afterwards and became a co-author. And so I want to talk to you about advertising, and I want to set some context. Before advertising on the internet, there was advertising before, and advertising really dates back to the 19th century. And one of the famous advertising pioneers, John Wanamaker, has a quote that's often mentioned in business schools, which is that half the money I spend on advertising is wasted. The trouble is I don't know which half. Now, this was, at the time, if you could imagine putting a newspaper advertisement out about a sale or putting a set of advertisements out, or more recently television and newspaper advertisements out, you have no idea if your sales go up to which ad people are responding and which of your advertising programs have been successful. And the story we usually tell about the internet is that that's no longer true. Because people click on ads, and you can tell if I put a particular ad down, how much, I have an ad campaign, I show an advertisement on the front page of Yahoo, I see how many people are clicking on that ad, and I know something about how the ads perform. But that's actually a simplification, because the internet actually has both kinds of ads on it. So here's actually I originally got involved in this because of a client among whose customers were newspapers that were advertising. And here's the Miami Herald. This is an example of an ad from last spring. Here's South Motors Oil and Wash $24.95. There's nothing to click on here. It's a traditional brand ad, and just the same old-fashioned kind of brand ad that you would have shown on newspapers half a century ago. Here's Brickell Heights. This is a tower that was getting ready to open, and they want people to be aware of this so that they will rent apartments in this newly to be built, or maybe at that time already built structure, and nothing to click on. These are just ordinary old-fashioned brand ads. Just to set some context, in the actual consulting project, the way that was described to me is, you have the newspaper has its salespeople go out to the local Ford dealer. The local Ford dealer is going to have a sale for the weekend. The newspaper is selling, the representative of the newspaper is selling some ads to this local Ford dealer, and after he's sold some ads for the print edition, this was 5 years ago or so, after he sold some ads for the print edition, the salesman would say, by the way, you really ought to buy some ads in our online edition too. We have, now a large fraction of our customers who are reading our paper online. And he'd sell basically the same ad online as he was selling in the print edition. Now, of course, you all know that we also have these new-fangled or new-fashioned performance ads. These are, here's an ad, your social network United, learn more, and you click on it, and off you go to do something. Or this ad over here, which is a savings account offering the amazing rate of 0.95%. Only in modern times is that an amazing rate. And if you click on it, you can sign up for a savings account. So these are the new-fashioned performance ads. And these guys have really pretty good information about where they place their ads, about what the performance is. Okay, so I want to distinguish in this talk between these two types of ads, what I'll call brand ads and what I'll call performance ads. By brand ads, I mean ads where the goal is awareness and image, and where the traditional advertising objective is reach and repetition. Disney has a movie that's going to open this weekend. It wants millions of people to become aware of it. It wants to reach some numbers of millions of people and to have them see 4 ads. So that they see it repeatedly and become aware and start some buzz going, and they get real attendance over the weekend. It's targeted to a large group, the large numbers of impressions, typically the guaranteed delivery, which is that I have a contract that says I'm going to get 1 million impressions or 5 million impressions, whatever it is. It could be Ford's weekend auto sale or Disney's movie opening or a shopping center's location that advertise in that way, as opposed to the kinds of ads that you guys more often think about, where you're trying to get some measurable action. You want somebody to click on the ad, to fill a form, to buy something. These ads are targeted to an individual, often based on cookies on the individual's computer. The number of impressions is often smaller. I want people who abandoned a shopping cart at my store. I want them to come back and complete the purchase. It's a small number of high-value impressions rather than millions of low-value impressions. They tend to be targeted and bought one by one these days at auction. So Hertz for car rentals, Amazon retargeting people who have left something in the store, Quicken Mortgage maybe it's targeting people who have recently searched about mortgage refinance and read an article about mortgage refinance or visited a site about mortgage refinance. They'll be targeting very distinct, relatively small classes of individuals. So these are caricatures. I mean, real ads are not all squarely in one of these two categories, but this represents a real distinction that's present on the web. Okay, so there's a danger of adverse selection here. That is, the brand advertisers are selecting impressions often en masse. They receive deferred and aggregated data about the performance of a whole ad campaign. The Ford dealer doesn't really know which of the ads is bringing the customers in, and you can't easily distinguish low-performing ads and publishers. Whereas these performance advertisers are using private cookies. They receive immediate, detailed data. They can quickly identify low-performing ads and publishers and stop using them. So if the value of ad impressions is positively correlated for both types of advertisers, brand advertisers may suffer adverse selection. It could be that on that website that I'm looking for desirable ads. There are people who visited my store, but I'm also preferring to target high-income people or people who I know are responsive to advertising from information I have about them. And if I'm picking off those ads and leaving for you the low-income people and the people who are not responsive to advertising, you're not too happy about that. Okay, so this is what we in our group call not quite optimal market design. We're interested in robustness. If you follow the literature on optimal mechanism design or optimal market design, at least within economics, it's mostly about writing down an optimization problem with well-specified parameters, and more in the spirit of things that you guys often do in computer science. We're looking for things that perform well, for a market design that performs well over a wide range of distributions. And I'll give you some ideas about that shortly. Okay, so here's the model we're going to be looking at. There are n+1 advertisers in this model. So I'm imagining that you're, like in the example I gave you, the Miami Herald has some space to show on its page, and n is greater than or equal to 2. The value to one of these guys is going to be a brand advertiser. That is, if I show a brand ad, it's going to be that Brickell Towers ad that I showed. If I show a performance ad, it's going to depend on who wants that impression. And the value of an impression to an advertiser is going to be assumed to be this number xi, which is the product of two terms. It's c, which is a random variable that we will call the common value factor. So if you have somebody viewing the page who has high income and is responsive to advertising, and generally that's a generally high value person for everybody. And mi, which is the match value factor, which is idiosyncratic. It has the I subscript. It means that for advertiser I, this guy's a particularly good match or not, depending on whether mi is high or low. The assumptions are that advertiser 0, the brand advertiser, doesn't really observe his value. He just has he can't tell. He knows the performance of the whole ad campaign, but he can't tell the value of a particular impression. The performance advertisers do observe their values. The common value factor, and so these are these are, sort of caricature the example I showed you. Here's an important assumption. The common value factor is statistically independent of the vector m, the vector of match value factors. Okay, so we're going to break this up into, on the one hand, variation due to common values, and on the other hand, variation due to match values. And the problem that the brand advertiser has is he's worried that the performance advertisers are bidding high and taking away impressions with high values of C and leaving impressions with low values of C. So the market design challenge, we want to compare the restricted worst case performance of different mechanisms on efficiency grounds. And I'm going to consider the following mechanisms to do the comparison. The first is going to be a benchmark that's theoretically not achievable. It's what we'll call the omniscient mechanism, in which you actually observe C. And you can eliminate adverse selection because you know what C is, and you can assign the items efficiently. The second is what we'll call the optimal mechanism, which is going to be a Bayesian optimal mechanism, in which what the market designer will do is try to maximize efficiency subject to incentive constraints that are familiar in this group. The third is the second price auction, which is a kind of auction that is commonly used for these things. And the fourth is our new modified second bid auction, which is what this talk is really about, in which the highest performance bidder wins if the ratio of the highest to the second highest performance bid exceeds a threshold. Okay? Otherwise, the ad goes to the brand advertiser. So that will be the new mechanism I'll be talking about. And so let's quickly run through these mechanisms. The omniscient benchmark we'll call OMN, in which the auctioneer observes both the bids and this common value factor C. So somehow or another, the auctioneer manages to observe that. And if the auctioneer could separately gather perfect information about the common value factor C and decide the allocation accordingly, ignoring any incentive constraints, then the value that we would get from each impression would be the maximum of either C times the expected value of M naught, that's the value to the brand advertiser, or X1 or ... Xn, the values to each of the brand advertisers. The expected value of that maximum is the value that we could get if we could observe C. Okay? The performance of other mechanisms are going to be compared to this. This will be in the denominator when we talk about performance of mechanisms. Okay? Bayesian optimal mechanism, which we'll call opt, we're going to have our performance advertisers bid, and we're going to have let's suppose that we have incentive constraints so that they're going to report truthfully. So what we'll do is, as a function of the truthful reports that the bidders make, we're going to assign the impression to bidder I with probability Zi of X. So X is the vector of values which are reported truthfully by the brand advertisers, and this is the probability that the item is given to X. PIX is I's expected payment given X. The goal is to maximize the total expected value, which is the sum I equals 0 to n of xi zi of x. And we're going to maximize this subject to incentive constraints and participation constraints. And we're going to let opt be the mechanism that does that.
So the zero bidder doesn't know x0?
It does not know x0.
So are you running an auction on the other guys?
Oh, so I'm sorry. So I should have an expected value of x0 no, actually here.
X0 equals expectation of M0?
No, I'm sorry. No, x0 is here. This is what I'm trying to maximize. I'm sorry. This is correct. This is what I'm trying. I don't know x0, and this zi is actually going to be the probability that xi wins given x, and I'm going to have dominant strategy incentive constraints for the performance bidders. But this is the value that bidder 0 gets when his value is. So this is the right objective. It's just that I don't.
You're running an auction on the brand,
brand advertisers, yes.
Performance.
Yes. Only the performance advertisers bid. Okay, we have a contract with the brand advertiser that says we're going to deliver, 1 million impressions over some period of time, and subject to some. Yeah.
So the performance advertisers observe X, but they do not observe C. And is that important whether they observe C?
We'll come back to that. So for now, yes, assume that the performance advertisers observe X but not C. Okay? So this decomposition is our decomposition, not necessarily their decomposition. Okay, so in an example, here's an example to show you how awkward this can all be. So suppose that the match values M1 through Mn are IID, that C can be either 1 or 2, we'll call this low or high, each with probability a half, that the match value can be 1, 2, or 4, each with probability a third, and that the expected value of M0 is between 3 and 4. Okay, this is just an example. Optimally, a performance advertiser N with Mn equal 4 would be assigned this impression, and otherwise the impression would optimally be assigned to the brand advertiser in this example. So this is what the solution looks like. It's a bit ugly. The expected efficiency maximizing assignment with 2 bidders is that if the highest, what is this? If the higher or the lower value. If x1 is between 1 and 2, and I think this, I've forgotten what notation I'm using. I think this means the larger of the 2 x's for the brand advertiser is either 1 or 2. That means that M1 is less than or equal to 2, and that's less than the expected value of M0. So we should, if the high bid is 1 or 2, we should give it to the performance advertiser. If x1 is 8, we can infer for sure that the highest value, match value is 4, and that's bigger than the match value of the brand advertiser. So in that case, the item ought to be assigned to the performance advertiser. If x1 is 4, then it could be that M1 is 4, or it could be that M1 is 2. We don't know which. So the assignment hinges on whether the expected value of M1 given x1 and x2 is greater or less than the expected value of M0. And so the assignment ends up depending on the second highest bid. If x1 is 4 and x2 is 1, then we can infer that M1 is 4, and we ought to assign it to the performance advertiser. If x1 is 4 and x2 is 2, then you can calculate that the expected match value is 3, which is less than that of the brand advertiser, so it ought to go to the brand advertiser. And if x2 is 4, it ought to go to the brand advertiser. It's all just algebra. But the point is that there's a statistical inference problem that goes on here, that you observe x1 and x2, and you're trying to separate and somehow figure out what is the match value and what's the performance value, and you assign the item accordingly. Okay, and the algebra just does that. The main takeaway is that this is a statistical inference problem, and so that highlights 3 concerns. First, opt is sensitive to detailed distributional assumptions. If we change the distribution, we're going to change the way we do the statistical inference. We're going to get a different looking mechanism. False name bidding. If we have performance advertiser N has xn equal to 4. If he could submit an additional bid with xn hat equal to 1, and we then did an optimal statistical inference, we would and assumed that these were actually independent bidders, we'd be saying, gee, if somebody has a value of 4 and somebody has a value of 1, that means the highest match value is 4, and this guy ought to win. So putting in an extra low bid could cause a bidder that was otherwise losing to become a winner. Adverse selection, the brand advertiser in this case wins 4/9 of the high value impressions of the high value impressions, but 7/9 of the low value ones. Forget that high, that's low. That's most problematic if the brand advertiser feels uninformed about the impressions and who else may be bidding. Brand advertiser doesn't really know. He just wants some assurance that he's getting a fair set of impressions. Okay, so that's what opt looks like. Here's a modified second bid auction, and I'm going to begin by characterizing it by its properties. So where did we come up with this idea of taking the ratio of the highest to the second highest bid? So this is going to be an axiomatic characterization, and then we'll do something numerical. So a mechanism is said anonymous among performance advertisers if, and I'm going to omit the details of the definition. These things are all obvious enough, and I'll say them in words. It's anonymous if it's independent of permutations. That is, you switch the order of the performance advertisers. The highest performance advertiser wins, for example. It doesn't matter what the labels are on the performance advertisers. It's strategy proof if it's a dominant strategy for everybody to report their value truthfully. These are familiar ideas. It's fully strategy proof if, in addition to being strategy proof, it's both bidder false name proof, which means the bidder can't benefit by submitting additional bids, and publisher false name proof if the seller can't benefit by submitting low bids. That's what we're going to call fully strategy proof. And it's adverse selection free if for every joint distribution on the common value factor and the match value factors for which these things are statistically independent, Z naught of X, the probability that the item gets assigned to the brand advertiser, is statistically independent of C. Okay, so that's adverse selection free. And a modified second bid auction, a direct mechanism is a modified second bid auction if for some alpha greater than or equal to 1, if the ratio of the highest to the second highest bid is strictly greater than alpha, then the highest performance advertiser wins and pays alpha times x2. And otherwise, the brand advertiser wins and pays its contract price. That's what we mean by a modified second bid auction. And then the theorem is a deterministic mechanism is anonymous, fully strategy proof, and adverse selection free if and only if it's a modified second bid auction. Okay, that's the characterization theorem, and actually I should make it. Let me make this intuitive for you. Let's go back to the conditions. Okay, it's anonymous among performance advertisers. That means it's got to be symmetric in the bids of the performance advertisers, free of permutations. Modified second bid auction clearly has that property. Strategy proof. So it has to be a dominant strategy to report truthfully. And I think many of you know, certainly the economists know, and I think probably it's familiar to most of you as well, that the only time a mechanism in this assignment-unassignment context is strategy proof is if for each bidder there's a threshold that depends on other bidders' bids such that it wins if its bid exceeds that threshold. And in that case, it pays the threshold price. These are called threshold auctions or threshold mechanisms. Modified second bid auction is a threshold mechanism. The highest bidder wins if and only if his bid exceeds alpha times the second highest bid. There's going to be just one winner. Alpha times the second highest bid is a threshold. If he bids higher than that, he wins. If he bids less than that, he loses. It's in his interest to report truthfully, because if his actual value is higher than the threshold, he wants to win. He wants to, at the threshold price. If his actual value is less than the threshold, he wants to lose. And so it's a dominant strategy to bid truthfully. And all of that can be written down in symbols and made formal, but it's actually all very familiar threshold auction stuff. Fully strategy proof, well, now if you start sticking in some low bid, if you're the winning bidder, you're going to have to pay alpha times x2. If you put in a higher bid, if you put in a low bid, it doesn't affect anything. If you put in a bid that's higher than the second highest bid, all you can do is make yourself lose or pay a higher price. So it can't be in the interest of a bidder. In general, in order to be fully strategy proof, what this ends up implying in the formal proof of the theory is that the outcome can only depend on the two highest bids. If the outcome depended on any bid other than the two highest, either the publisher or the bidder would have some interest to put in that third bid and manipulate the price up or down. So this really just this extra condition really just means that the auction outcome depends only on the two highest bids. And adverse selection free. Now here the idea is that if you take a look again at the condition, x1 is c times m1 and x2 is c times m2. So if you take a look at this ratio, the c cancels in the numerator and denominator, and you just have m1 over m2. So the event that the performance advertiser wins is statistically independent of c. That makes it adverse selection free. And you can show generally that well, I won't even go into what you can show generally. This is the, you can see that's a pretty special condition. You can, if you have something that depends only on the first two bids, this is the only mechanism that's going to give you adverse selection free, the only anonymous mechanism that will give you adverse selection free. So, and all of that, the proofs are written down in the paper. Okay, so that's the axiomatic characterization. That motivates the why we did this. I should say that we had some discussions with our client about what they thought were reasonable models of adverse selection, of adverse selection in auctions. This multiplicative model, there's nobody's going to have. There's never going to be unanimity about what's a reasonable model of how common value and match value factors affect things. But this multiplicative model had great appeal to the people I was talking to, so we settled on this model. It does seem that there are some impressions that are just pretty valuable because people are responsive and they have high incomes, and the match value does seem to be a separate kind of factor. But I don't want to defend that model too vociferously. It's just a model. What I do want to do is compare the modified second bid auction with parameter alpha, the second price auction with reserve R, and the omniscient mechanism, so that we see what these things look like. And for the comparison, we're going to evaluate both mechanisms in a worst case over a limited family of environments. So we're going to assume that M1 through Mn are IID from some distribution, that C is drawn from some distribution F, C is drawn from some distribution G. There's at least two bidders. And the other than that, n is arbitrary, and em naught is some non-negative number that's arbitrary. And so here's the theorem about the comparison. This compares second price with reserve and modified second bid to in the worst case with these very weak these independence type distributional assumptions. Assuming Nash equilibrium bidding by the brand advertiser, both modified second bid and second price have similar worst case performance. If you take a look at the value of the modified second bid auction divided by the value of for the best, for a parameter that's optimized for the environment, but then you take the infimum over environments, the infimum over distributions F, distributions G, numbers of bidders N, and means of the performance advertisers, you get a half. And the same thing gives you a half. The second price with reserve does the same. Okay? But if you further restrict, if you imagine that that match values are drawn from fat tail distributions, you imagine that what's really going on in brand advertising is that there's a small number of impressions that lead to most of the value. So now I'm talking about power law distributions. So if you restrict F and G to be drawn from power law distributions, and actually, for this, you only need to restrict F. I probably should have left out the and G here. If you restrict F to be drawn from power law distributions, then I think if I'm going to do both of these, I need F and G. Sorry. So F and G to be drawn from power law distributions. Then for the second price auction, this thing remains a half. But for the modified second bid auctions, this goes up to 0.95. Okay. So what's going on here? Let me try to give you some intuition about what's going on here. So how can this thing jump up to 0.95? This is the surprise, right? This is the one thing that most needs explanation. And so what's going on here is that in the modified second bid auction, what we're looking at is the ratio of the highest to the second highest bid. And when we get a really good match every once in a while, the ratio of the highest to the second highest bid is going to be really big. These match values are statistically independent. And most of the value comes from extreme values of the distribution. What I'll show you formally, in fact, is that the ratio, let me remind you of some math. The power law distribution, random variables have a power law distribution if and only if their logarithms have exponential distributions. Okay, and so exponential distributions I know are very familiar to people. So what that means is if you take the maximum of a bunch of exponentially distributed random variables and you take and the second maximum, the difference between the max and the second max is also exponentially distributed with the same distribution, right? That's familiar from waiting times and queuing theory and so on, right? That the last after you've received, if you got just one person left who's waiting to be served, the remaining waiting time is still conditional on the second longest is still exponentially distributed with the same distribution. So similarly for ratios in power laws, if you take the ratio of the highest to the second highest value, that has a power law distribution with the same parameter. And so the ratio of the highest to the second highest bit, almost all of the value there lies in the very high values of that parameter. So when this guy wins, you're picking up most of the value. You're picking up most of the high value cases. The guy with the highest value to the guy with the second highest value, that ratio will be high in almost exactly the same cases where there's a very good match, and where the reason that the bids are high is that there's a high common value. Where the reason that the bids are high is that it's a really good person to advertise to, then all of the values will be high. And if the ratio is roughly 1, that means, well, it's a good item to give to the match value to the brand advertiser, and not an especially good item to give to the brand advertiser. And I've got here was the F and G thing. For this INF, I've shown in red that what I need is that the match value distributions have a power law. The intuition I just gave you involved match value distributions being a power law. The G could be anything. Whereas for this one, I could have left this out. I've added the restriction that the G is also a power law distribution. That, if anything, should make this higher. But I've said even restricting G to be in power law distributions, this is still just a half.
In the second case, is it the case that you get most of your welfare from just performance guys?
No. So this is so this depends on. So that's not the case. In fact, it could be that the expected value of M naught is 0, for example, and all of the welfare comes from the. Oh, I'm sorry. Could be that the expected value of M naught is infinite. It could be 0. It could be infinite. This is any expected value of M naught.
It could be infinite in this thing?
It could be infinite. Or
for any constant, you expect one of the power laws to be...
So if the expected value of M naught is low, then almost all of the value comes from the brand advertisers. If this is high, then almost all of the value... Sorry, I said it backwards. If this is low, almost all of the value comes from performance advertisers. If this is high, it comes almost entirely from brand advertisers. Wherever you are, and no matter what power law you have, and no matter how many bidders you have, the worst case is 0.95.
Paul, intuitively, is it true that alpha will be increasing in expected M naught because that's how you're going to get the value out?
Yeah. Yeah. So what will happen is that if you have ads, some class of ads that you think is particularly valued to brand advertisers, you want the brand advertisers to win a lot of those ads. You set alpha high, and so this involves the newspaper in the example I gave you adjusting alpha to the mix that it thinks it wants of performance and brand ads in order to get to optimize. Maybe that was the answer to the question. So thank you for that, Steve. Okay, revenue performance. If you fix a number of bidders n and assume that the publisher shares the rents from the brand advertiser in any fixed proportion. So you imagine we have this brand advertiser that we're writing a contract with, and we're sharing the value so that some fraction goes to the performance advertiser and some fraction to the brand advertiser. And if F's from a power law distribution, then there's some alpha so that the modified second bid auction also achieves actually 94.8% of the expected revenue from the corresponding revenue maximizing strategy, which we'll call Rev Max. So it does very well on revenues as well. Okay, and that I'm told that I was at the end, so I have a few minutes for questions. Kevin.
So it seems on the face of it that the shape of the functions that you assumed in evaluations might really be driving the result here. That you've said that x is c times m. Yep. So you have this multiplicative relationship, and then and also in the power law distribution, you again have this very special multiplicative relationship, and you end up finding that something based on ratios works really well.
Yep.
I imagine, in your actual newspaper example, you don't know that precisely this form evaluation relationship holds. Do you have some intuition about why you expect this to degrade nicely in situations that aren't exactly like this?
So where I actually started this before Nick got involved, by the way, where we actually started was the question of, is it even possible to have an auction where the participants bid that's adverse selection free? And so I think of this thing as having been built in two parts. There was the part where we said, well, gee, if we had this multiplicative relationship, if this is the way you guys conceive the value, that there's high value impressions and good matches, and that it's the product of those two, then it is possible to achieve adverse selection freeness by taking, and we actually characterize the whole class of functions that do that. And then if you add false name proofness, there's only one function left. It's this ratio of the highest to the second highest bid. And we sort of had stopped there. And then it was, so that's one piece. It's a separate piece. Then the power law distributions, we had examples that we'd done with power law distributions that performed remarkably well. And so we sort of, our intuition for why it might perform well is exactly what I've described. And you've asked about the functional forms. The functional power law is a way that we formalize the idea that most of the value comes from a few good matches. That was what we were trying to do. How could this degrade badly? So we know some cases where it degrades badly. So suppose that you have power law type distributions. We have fat tails, so most of the value comes from good matches. But let's say we have two jewelry stores, and you happen to be a really high value customer for jewelry stores. So we get too high bids from jewelers. Then the ratio is not going to capture the fact that this guy is an especially good match for jewelry stores. So we know something about when it degrades, and it does come from intuitive analyses of what the mathematics is trying to capture. Namely, a lot of value comes from from very good matches, and those matches tend to be unique. That seems to be what it takes for this to perform really well.
So you have two theorems with alphas in them. Are they the same alpha, or?
So the alphas are so two theorems with alphas in them. Let's go back to the theorems. So the two theorems. Okay. Where's the theorem? Okay.
Well, really, I'm asking revenue and.
Oh, you're asking about the revenue and the efficiency, and the answer is essentially yes. Essentially, it's the what happens is that I'm giving the. So is it the same No, I'm sorry. The answer is essentially no. Let me switch that. Let me switch that answer. There's a sense in which it's essentially yes. That is what we do. Is once you fix the fraction of value that is going to the that's being captured by the advertiser. He just ignores the rest of it in his objective, and then the problem looks just the same as the other problem, but with a lower value of EM naught. Right? He's saying that match isn't so valuable to me. It's because the brand advertiser is getting most of the value, so I'm going to resolve the problem with a lower value of EM naught, and then I'll get a lower value of alpha. Does that answer your question?
Possibly, but I don't understand.
All right.
I have the same question.
Yeah.
But what I understood that answer to say is the rev optimal alpha is just the same as the other alpha, except solved for a
different problem.
A lower M value.
That's right. Yes.
Which could have a massive impact on the efficiency. We don't know.
Yeah, so all of that depends on delta. If I'm not very good at bargaining with the brand advertiser, so I get very little revenue from the brand advertiser, then I'm going to bias the, and if I'm trying to maximize revenue, I'm going to bias the auction in favor of the performance advertisers. If otherwise, if I'm very good at bargaining with the brand advertiser, I'll put in the opposite sort of bias. If it's sort of neutral, that I get the same fraction from both the brand advertisers and the performance advertisers, then I'm interested in maximizing efficiency. So to the extent that my ability to extract revenue from the brand advertisers is different than my ability to extract revenue from the performance advertisers, I will be biased away from efficiency in the corresponding direction.
So it would be really nice if there was a corollary that said, if delta is 0.94A,
Yeah.
that revenue, that you get at least that in the revenue. That is, you capture 94.8% of the.
Oh, I see. So we could have a theorem that got the efficiency and revenue aligned. That's what you. Yeah, got it. Yeah, that would be interesting. I'll take a look at that offline.
So I think coming back to the comment about jewelry stores, so the independence I think is really important, right?
Yes.
Avif and I both have our farming video game that we're trying to sell, and we're basically the same game. We're always bidding about the same amount. So the brand advertiser is going to get all of those.
Yes, that's right.
And Richard has this more unique puzzle game, and so he wins all of those. So it's really not representative anymore what the brand advertiser gets.
Right. So there's a lot of things that could make this not representative empirically. I mean, some of this stuff is empirical, whether these are good assumptions or not. There are other things that are going on in this industry, that have become increasingly important since we began this research. You have these demand-side platforms that are not putting in all the bids. They're just putting in a bid for one of their clients and withholding bids for other clients. There are all sorts of things going on that could make this not match the current reality. So I think what's important is exactly what we're talking about, to identify what the characteristics are that cause it to perform well or badly, to take so that we understand it well, and then to do things empirically and see how it works on the data.
Would it be useful to look at where the big gap is? So what Conrad was saying was that if the top two are advertisers are very high, then you would give it to the brand advertiser. But what if there are K very high ones and then there's a very low one? There's a big gap.
Yeah. So the reason, so it turns out in our model, if you didn't impose false name bidding, then it would be optimal to, if you didn't require that the thing be fully strategy proof, that there be no incentive for false name bidding, then the optimal mechanism would depend on the ratio of the highest to the lowest instead of the ratio of the highest to the second highest. You can demonstrate that with power law distributions. So it's a sufficient statistics result that's in there. So it would solve some of that problem if there was correlation, but it would also expose the auction to false name bidding, which we think is a serious problem in an anonymous market.
And what if you had some sort of similarity score between bidders, right? So you would say that Avif and I are so similar that you would make alpha really small in that case. So
yeah, so I mean, you can imagine variations like that. Again, I've imagined an anonymous market. You're now dropping anonymity and saying, well, if we know something about the bidders, maybe we can undo the problem in that way, and maybe so.
Let's take further questions outside. Thanks again.
Thank you.